Good morning. We are going to be looking at what's happening underneath the sea. In fact, originally, we thought it was a big, flat, vast desert like this picture here. That's what we thought it was. We came to find out later that it had all of these different features. Here's our continent, and we've got the continental shelf, which, by the way, is part of the continent that happens to be underwater. It's the same type of rock. And then you've got continental slopes, and you've got abyssal plains, which are flat areas. You have volcanic island chains. You've got abyss, really deep areas. You've got trenches, can be even deeper areas. You've got seamounts that break through and goits that haven't broken through. And you've got the mid-Atlantic ridge. There's all this topography underneath the water we didn't know about. In fact, we're not a perfect sphere. If you look at the oceans without water, it's a crazy looking thing. So if we look at the Earth without its water, you're going to notice that it is not a perfectly round sphere. We have a lot of topography above ground, and we have a lot of topography underneath the oceans. So how do we start to figure this stuff out? Well, if we go back to last unit, just a quick review. Remember, our mid-Atlantic ridge is a divergent zone. Our trenches are convergence zones, and that's where it's coming together. And remember, we can have that transform fault, that shearing force, where, like the San Andreas, where remember California is not going to fall into the ocean; it's going to slide up the coast, and it has a better shot of hitting Alaska than it's falling into the ocean, and that's still a long ways off. And all of this started because of a man named Alfred Wegener. He lived from 1880 to 1930. No, you don't have to know that for the test, but it's just for your general background. And he was born in Berlin. He was an expert in meteorology, geology, and astronomy. He had a lot of interests. He actually died in Greenland. And just a quick reminder, Greenland isn't green. See? Greenland, icy. Iceland, green. They flipped them back and forth because they didn't want people coming to their, paradise. So they flipped the names. And if you're looking for it, here's Canada, here's Greenland, and there's Iceland. So Wegener came up with a theory of continental drift, and he was ridiculed for it because he had come up with all this evidence that was really good evidence, but he didn't have a mechanism for the continents to move. And because of that, he could have died. His name would have gone and no one would have known it. You would have never heard of a guy named Alfred Wegener if it hadn't been for a guy named Harry Hess. But in 1912, he proposed that there was a large continent called Pangaea that existed and then split into the continents we have today. And he had fossil evidence. He had the shape of the continents, and he had glacial striations and mountain ranges and all of these things that seemed to fit together. But because he couldn't come up with that theory, that mechanism that made it work, they really didn't think it was true. And a geologist today is like, how could you not believe that? But it was just inconceivable that something as large as a continent could move, because we are splitting apart from Europe right now, but it's about the same rate your fingernails grow. It's not very fast. But Wegener pieced together all this information, and we've got some mountain belts. They don't show up on this one, but this fossil right here is called the Glossopteris fern, and it's a tropical plant. Well, if you know anything about Antarctica today, you're not going to have tropical plants there. But we have fossil evidence, and if you line the continents up, the fossils line up too. Glossopteris actually goes through Australia, all the way through Antarctica, up through India, Madagascar, into Africa, and South America. The mesosaur is a land creature, and the fossils are from the same time period, but they couldn't have swum across the vast ocean to get to each other. And we usually also know that things don't really develop in isolation. They at exactly the same time and exactly the same way in exactly different places. So it's a pretty good piece of evidence. And if you look at how the continents fit together, their shapes kind of fit. But if you actually include the continental shelf, they actually fit together even better. So this was some of the evidence. And we've also got some glacier striations that were coming in here. And if you look at the way the scratches go, it would make sense that we had a big ice source here flowing in this kind of direction. And he took all of that, but no one believed him. And it wasn't until this guy, Harry Hess, He was from Princeton University, but he was a naval reservist. You're going to see a quick video about the two in just a moment. But as he would go across ferrying goods from the Americas to Britain in the war effort, he left his sonar on. They used that to come into port, but he was a geologist at heart, and he wanted to see what the ocean was like. And he found the fact that we aren't this flat desert. He found volcanoes and ridges and big areas, but he's the one that came up with the mechanism for seafloor spreading. He found the mid-Atlantic ridge, and then they looked farther on the other side and they found the subduction zones. So without Hess and his having to be brought back into the war, he was a naval reservist, we may not to this day know it in the same way or as fast, but his science research allowed us to prove Wagner's theories. So as we look at seafloor spreading, we've got the whole tectonics thing going on. So that is what we're starting to get into, the fact that it just simply means the plates are moving. It's an active sphere. And the lithosphere, the toppermost layer, is sliding upon the asthenosphere. So that's where we're getting into the tectonic plates. And if you remember, we actually looked at the earthquake video where we could see that chain and where everything breaks. That convection current is really what's dragging the continents apart. And again, divergent seafloor spreading is happening at the mid-Atlantic ridge. And what's really cool is there's one place where that ridge goes through land, and that's Iceland. Iceland's getting bigger. It's actually growing. The North American plate is going obviously towards us. The Eurasian plate's obviously going towards Europe. And Iceland itself is actually actively getting bigger, but that also means they have a lot of volcanic activity. So subduction is the other part. Remember, if we get bigger on one side, we have to get smaller on another. So we have the world's most explosive volcanoes are found in those subduction zones. That's Mount St. Helens, Mount Rainier, Mount Shasta, all of those. The Cascade Mountains, the Andes Mountains go down into South America. And really what's happening by Seattle and up north of California, you have the Juan de Fuca plate, and it's actually being subducted under the North American plate. And that's those active volcanoes for the US anyway. So convergent means to come together. That's your subduction. And this is also where you get those really deep trenches, because as the plates come together, this one comes down and under because it's basalt rock, heavier than the mafic, less dense crust, but it kind of drags it down and you get this big V trench. And we can see that. We've been down to the Marianas Trench, which is the deepest and the one that we know of, and I believe now we've been there twice.
So we're down, yeah, so
So you've got the munch and the crunch. The munch is the subduction of the ocean plates under the continent or ocean, and the crunch is the collision of the continental plates, India running into Tibet and China, forming the Himalayan mountains. So without those mechanisms that Harry Hess helped identify, Alfred Wegener's theory wouldn't be here. So we, as I said in the video, we combined them all into one thing on plate tectonics.
We're following the destructive trail of the Krakatoa volcano to see if a future eruption could plunge mankind into an apocalyptic.
So what this is really talking about is those subduction zone volcanoes. Krakatoa in 1800s, I'll give you the date, which you won't have to memorize, by the way. You just need to know that it's happened. Had a massive eruption, and this is a subduction zone volcano. So this is one of the effects that you can get from it.
Question.
If you want to be a field geologist, you better be prepared to go to some beautiful places and some out-of-the-way places. So the one last force we haven't really talked a lot about is the San Andreas, which is that translation is a strike-slip fault. Remember, that's that side-to-side motion that they talked about. So what are some of the things we know? Well, if you compare the ocean floor crust, it's at most 200 million years old compared to the oldest land, which is in the billions, in fact, more than 3 billion years old. We can get Morton gneiss in Minnesota, which is 3.7 billion years old. And if you want to get older than that, go to the Canadian Shield, go to South Africa, or the Red Rocks in Australia. Our continental crust is so light, it's kind of floated up on top, and it hasn't been recycled as much as the ocean floor has, which is that dense basaltic rock, and it gets subducted, it gets recycled over and over again. So we have a really young ocean floor. So the law of conservation of the ocean floor says if we're making new at the Mid-Atlantic Ridge, we have to be recycling it somewhere else, and that's the Pacific Rim. And we talked about this in last unit, where we saw the video of a year of volcano or a year of earthquakes. And with that, we actually see the outline of the different plate. Here's the Nazca plate, here's the North American plate, the Eurasian plate, the African plate, the Arabian plate. Here's India slamming into Asia. Here's the Australian plate, the Antarctic plate. And, we've got the Caribbean. There's all these different plates. And here is that Mid-Atlantic Ridge running all the way down. This is divergent. It's showing you the direction of the motion of the plates. It's being running into each other here. It's moving away here. It's moving away here. It's moving up this direction. That's where we're saying this plate, this part on the San Andreas, is actually heading this direction. And if it continued that way in a straight line, which it could or could not do depending on how everything shifts, there's Alaska. So if we take Wegener's and Hess's ideas and add them together, we have the new ideas that really lends itself not just to continental drift and seafloor spreading, but the whole theory of plate tectonics. So evidence, fit of the continents, correlation of the mountain belts, diversity of species, and glacier formation. And we see here is what Pangea would have looked like. Here's where all the plates, the continents were together, and they start splitting into our current day. And again, remember the Glossopteris fern going through all those places that today just couldn't support it. The Mesosaur, all of these animals, if you fit them together, they fit really well. The shape of the continents. We've got mountain forming. Again, you're not going to find this same fossil here in South America as you are in South Africa that can't cross the ocean. It's a land-bearing fossil, so they correlate there. But there's also these things called striations. When glaciers move, they drag stuff along with them on the bottom, and rocks scratch rocks, taking away the soil, and they leave these deep scratch lines called striations. And if you follow them back, you follow them to the source of where the glacier started to move. And if we look at it, we have glacial striations that would make sense if you had a big body of ice here moving in this direction. But when you look at it here, it doesn't make sense compared to this one. It had to have been together. So that's just another piece of the evidence. We also have magnetic reversals that we can see at the Mid-Atlantic Ridge. When magma erupts, it's got free-floating iron particles, and as it cools, they usually align with orientation of the North Pole. But at the Mid-Atlantic Ridge, on either side, it's like bookend. You actually have this mirrored image on each side, and we see the reversals of our magnetic fields over time. So, you take Brunn's ideas with Wegener and Hess, and you get even more evidence of seafloor spreading. So the magnetic field flips back and forth, and we can see that striping here as a GIF of seafloor spreading at the Mid-Atlantic Ridge. As we go through, you can actually see the changing polarities, and it's mirrored on both sides. That's the really important thing. It's the same. As you move farther away from the center, this is younger with the same magnetic field position. As you get over here, it's older with the same magnetic field position as it is over there. And we see it diverge of what the Earth will do over the next 300 million years as the plates move, with the evidence we have of how the plates are moving and how we know subduction is happening. Again, it's an estimate, but it could be close. And it's interesting because you'll see as the continents themselves start to break apart sometimes, and you get water levels rising. widening of the Atlantic and the coming together of the repositioning